Hello everyone, welcome to module 7 on circular motion and gravity. So in this module we're going to discuss circular motion, Newton's law of universal gravitation, motion in space, and finally end the topic with torque and simple machines. So let's start with circular motion. So we're going to discuss how to solve problems involving centripetal acceleration, how to solve problems involving centripetal force, and finally explain how the apparent existence of an outward force in the circular motion can be explained as inertia resisting the centripetal force, more commonly called as the centrifugal force. So let's start with tangential speed. So the tangential speed of an object in circular motion is basically the object speed along the imaginary line drawn tangent to the circular path. So tangential speed depends on the distance from the object to the center of the circular path. And then the tangential speed is constant, we call that uniform circular motion. So let's take an example. So let's say we have a body that is under circular motion. Now this body under circular motion, generally when you, let's say for example at this particular point we left that body and there is the motion generally gets cut. So which means that the body is going to go travel in this direction. So the velocity with which it travels in that direction is called as the tangential velocity. So this velocity is called as the tangential speed. So this tangential speed depends on the circle's radius, and this is the one that is mainly important for understanding the circular motion. Now if this velocity Vt is constant, we call that motion a uniform circular motion. Now let's talk about the other type of acceleration called centripetal acceleration. Now what does centripetal acceleration look like in terms of the picture here? Now whenever the body is rotating around a circular path, it also has a velocity towards the center and it travels with an acceleration towards the center. That acceleration is called as the centripetal acceleration. So this acceleration where the mass is acting downward, the force is acting downward, but the velocity is coming forward, but the direction changes continuously. That change in the direction continuously causes it to create a centripetal acceleration. Remember here that even though the magnitude does not change, the direction does change. So because acceleration is a vector quantity, if there is a change in the direction, it means that acceleration will have to change as per the changes in the tangential velocity. So the changes that are happening in the direction of the tangential velocity create the centripetal acceleration. Now the acceleration of an object moving in a circular path at a constant speed due to change in direction is generally called as centripetal acceleration, and this is given by the formula AC equals Vt square by r, where Vt is the tangential speed and r is the radius of the circular path. So remember this formula, Vt square by r. So what happens at each point here is that you have, even though the velocity is the same, the direction changes because there is a change in the direction. So there you create a net velocity which is going to be different from the two other velocities, so which creates the centripetal acceleration. So and one another important part to remember is that the centripetal acceleration is always directed towards the center of a circle. So this is another important point to remember. Now you have also seen centripetal acceleration results from that. It generally results due to the change in direction. Now the point is, in a circular motion, an acceleration due to change in speed is called tangential acceleration. So there are two types of accelerations combined here. So one is the acceleration when the body is traveling in this direction along the path. So this direction is the tangential direction and this direction is the centripetal direction. So this is the centripetal acceleration and this is the tangential acceleration. Now combining both accelerations gives you the total acceleration of an object. So to understand the different parts, think about it like a circular track. So on a track, you notice that you have two velocity, two accelerations. One is the acceleration due which you're going in the direction along the circular path, and the acceleration along the towards the center of the circular path, resulting in the combined acceleration. So to calculate the total acceleration, AT, so A is given as the square root of AC square plus AT square. So this here is the total acceleration. For a body traveling with uniform velocity, so for a body traveling under uniform circular motion, so uniform circular motion meaning that here Vt is constant. So the total acceleration is going to be AC square plus AT square, because the Vt is constant, so AT is going to be 0. So which means that the total acceleration becomes the centripetal acceleration for a body under uniform circular motion. Now we discussed acceleration. Remember that acceleration of an object also creates force. That force here is called as the centripetal force. Now consider a ball of mass m that is being whirled in a horizontal circular path of radius r with constant speed. Now the force exerted by the string has both horizontal and vertical components. Now the vertical component here is the gravity, so the force of gravity, and the horizontal force is the force of the centripetal force, and the combined velocity here, the net force which is directed towards the center of the circle, is called as the centripetal force. So you have the vertical component equal and opposite to the gravitational force, and therefore resulting in the horizontal component which is the net force, so which results in the centripetal force. So when a body goes in a circular path, it not only creates an acceleration towards the center, it also creates a force towards the center, and that force is generally called as the centripetal force. Now combining centripetal force, we can use Newton's second law. So we know that from Newton's second law, we can write F equals ma. So we are talking about the centripetal force, so mass does not change, acceleration becomes the centripetal acceleration. So we know the formula for centripetal acceleration is Vt square by r. So we can write the force as m Vt square by r. So this here is the formula for the centripetal force. So centripetal force is simply the name given to a net force on an object in uniform circular motion. Remember that this is the net force of two forces, the horizontal force and the vertical force. Now, any type of force or combination of forces can provide this net force. For example, you can have friction between a race car's tires and a circular track is a centripetal force that keeps the car in the circular path. Another example is the gravitational force is a centripetal force that keeps the moon on its orbit. So every force, the net force itself, we call it a centripetal force, remembering that centripetal force itself is not something different. It can be caused by any type of force or a combination of forces. The idea here is that the force should be directed towards the center, and if that force is directing towards a rotating object towards the center, then that force is generally called as a centripetal force. Now, if the centripetal force vanishes, the object stops moving in a circular path. This example is, let's say for example, when you have a rotating object suddenly whirled, it happens to go in a circular path, in a straight line path. Now, there are two cases that we can consider. If the ball breaks at the position shown in A, the ball will move vertically upward in a free fall. Now, if the string breaks at the top of the ball's path, as in B, the ball will move along a parabolic path. This is mainly due to the fact that you have gravity, the force of gravity acting at two different directions. Here, the force here acts vertically upward. So because the force is being directed upward, the acceleration due to gravity on the object is vertically downward. Here, it's still vertically downward, but think of it like a projection of a projectile. So think of it like a parabolic object thrown like a projectile, so resulting in a parabolic path. So let's try and understand how to describe a rotating system. So to better understand the motion of a rotating system, consider you have a car traveling at a really high speed and approaching an exit ramp that curves to the left. Now, when you take this consideration, as the driver makes a sharp left turn, the passengers slide to the right and hit the door. What causes the passenger to move towards the door? So remember this here is that we know that centripetal force is always an inward force or a center force. So which means that there is some force that is acting here that is pushing the person away from the path. This type of force is thinking about this as the car enters the ramp and travels along a curved path. The passenger, because of inertia, tends to move along the original straight path. Now, if a sufficiently large centripetal force acts on the passenger, the person will move along the same curved path that the car does. The origin of the centripetal force here is the force of friction between the passenger and the car seat. Now, if the frictional force is not sufficient, what will happen here is that the passenger will slide across the seat as the car turns underneath him. So, let's take a visual example of this. So, let's say, for example, you're on a circular track. So, let's say you're on a circular track and you're right here inside the car. Now, what will happen here is that as you sit in the car, you will be pushed directly outward. The reason you're being pushed outward rather than being inward, the main reason mainly is because of your inertia. So the inertia is not sufficient. So the centripetal force is not sufficient to pull you inward. So the inertia on your own body will try to push you outward. Remember that this is not a force, but this is rather the inertia that is trying to play its game. And because the frictional force between you and the car seat is not sufficient, your inertia will push you outward. This inertial force is called as the centrifugal force. So this type of inertial force that pushes you outward, this type of inertial force that pushes you outward is called as the centrifugal force. So remember here is that there is no something called as a centrifugal force that actually tries to push you away. It's more of the inertia not having enough energy to balance the centrifugal force, resulting in the motion. So any force that pushes you outward, when the net force is not sufficient to pull you inward, we call that a centrifugal force. So next, let's go into section 2, Newton's law of universal gravitation. So in this, we are going to explain how Newton's law of universal gravitation accounts for various phenomena, including satellites, planetary objects, falling objects, and the tides. And finally, apply the Newton's laws of universal gravitation to solve problems. So, what is gravitational force? Generally, orbiting objects are generally in free fall. So, to see how this idea will work, we can use a thought experiment that Newton developed. Consider you have a cannon sitting on a high mountain top. Now, whenever you're increasing the speed, at some point, what will happen is that the body will not come to the ground, but will rather graze the size of the earth. For example, let's say if this is the earth and you have a cannon right here. And let's say you're projecting the object. So let's say if you started with an initial speed and this is the object speed. Let's say you gave it some more speed and it raised the object right here. Now when you increase it to a certain speed, what will happen is that that speed will cause such a change that the object will rather not come but rather trace along the path, resulting in a circular orbit. So even though all the object is in a free fall, it does not have the Earth's gravitational field does not have enough energy to actually attract it. But what will happen here is that the object will rather take the effect the same in terms of a free fall, but rather circle around the Earth to make sure that it doesn't fall back to the ground. This here is the thought experiment that Newton developed to understand gravitational force. So the centripetal force that holds the planets together, planets in orbit, is the same force that pulls an apple towards the ground, which is the gravitational force. Now, gravitational force is a mutual force of attraction between the particles of matter, and gravitational force generally depends on the masses and the distances between them. So combining this, Newton formulated the Newton's law of gravitation, where he said that the force of gravity is proportional to the product of their masses. So let's consider you have two masses, m1 and m2, and they are separated by a distance r. So let's say we have two masses, m1 and m2, and they are separated by a distance r. So so Newton's law of gravity basically states that the force of gravitation is proportional to the product of the masses, and it's inversely proportional to the square of the distance between them. And combining these two, we get Fg proportional to m1 m2 by r square. So Fg, when you remove proportionality, you get uppercase G m1 m2 by r square, where G here is called as the universal gravitational constant. So where G is here is called as the universal gravitational constant, and that value is 6.67 times 10 to the power negative 11 Newton meter square per kilogram square. So this is the value for the constant, and this here is the actual explanation for the Newton's universal law of gravitation. So Newton developed basically stated that it's proportional to the product of the masses and inversely proportional to the square of the distance between them, more commonly known as the inverse square law. So from this you understand the gravitational force. Now the gravitational force between the two masses exert each other are always equal in magnitude and opposite in direction. So this is a simple example of the Newton's third law. So one example is that the Earth-Moon system. So as a result of these forces, the Moon and the Earth each orbit the center of the mass of the Earth-Moon system, because the Earth has a much greater mass than the Moon. So this center of mass lies within the Earth. So you have the force of mass of the Earth and the force of mass of the Earth and the force of the Moon on the Earth and the force of the Earth on the Moon, all both equal the centripetal force between them. Because the force becomes equal, it will never fall back onto the Earth, and resulting in the circular motion around the Earth. So this is the idea behind the universal law of gravitation. Now, how do you apply universal law? So most commonly, all the natural phenomenon generally accounts to the law of gravitation. For example, oceanic tides can be tied to Newton's law of gravitation. So high and low tides are partly due to the gravitational force exerted on Earth by its moon. Now the tides result from the difference between the gravitational force at the Earth's surface and at the Earth's center. So because the distance between them is different, so therefore resulting in the change in the gravitational force, resulting in high and low tides. So without moon there is no tides. So Cavendish also applied Newton's law of gravitation to find the value of G and the Earth's mass. So when two masses, the distance between them and the gravitational force are known, so we can always calculate the Newton's law of gravitation. So once the value of G is known, the law can also be used to finally find Earth's mass. Now, how do you apply the law of gravitation? So gravity is generally called as a field force, which means that it doesn't need any physical contact for the force to apply. Now, the gravitational field strength G is given as Fg by m. So therefore, the gravitational field G is a vector with magnitude G, and that points in the direction of the gravitational force. Now, the gravitational field strength also equals is generally equal to the free fall acceleration, which is about 9.81 on an average of 9.81 meter per second square. Now, so we know that weight is mass times gravitational field strength, so which is G, so which is basically Fg equals mg. Now G can be written as Fg over m. So G here, Fg here we can calculate from Newton's law of gravitation is m times me, which is the mass of the Earth, by r square over m. So m gone, so G can be written as G mass of the Earth by r square. So where you can consider m and r as the mass and radius of the Earth, and based on the radius we can calculate the value of G as well, so resulting in the value of G. So next let's come to section 3, motion in space. So in this we are going to try to describe Kepler's law of planetary motion, relate Newton's mathematical analysis of gravitational force to the elliptical planetary orbits proposed by Kepler, and finally solve problems involving orbital speed and period. So let's start with Kepler's law. So Johann Kepler was the first one to describe the motion of planets using his three laws. So let's look at each of these laws. So first law states that each planet travels in an elliptical orbit around the sun, and the sun is at one of the focal points. Second law is that an imaginary line drawn from the sun to any planet sweeps equal areas in equal time intervals. And the third law states that the square of the planet's orbital period is proportional to the cube of the average distance between the planet and the sun. So let's start with Kepler's laws. So Kepler's laws were developed a generation before the Newton's laws of universal gravitation. And Newton demonstrated that Kepler's laws are consistent with the law of gravitation, and that the fact that Kepler's laws closely match the observations gave additional support for Newton's theory of gravitation. So let's start with Newton's second law, the Kepler's second law. So Kepler's second law basically says that if you draw an imaginary line, it sweeps equal areas over equal amounts of time. So for example, if you consider the amount of time, let's say that it takes delta t1 to go to trace an area of a1 and delta t2 to trace an area of a2. So it says that if the time is equal, so if the delta t1 equals, so if delta t1 equals delta t2, so which basically states that a1 equals a2. So the one that is closer will trace more area, than the one that is farther will trace lesser area. But the amount looks different, but even though the actual area is exactly the same. Next, let's look at Kepler's third law. States that the square of the orbital time period is equal to the cube of the distance between the planet and the sun. So the constant removing the proportionality is 4 pi square by gm, where m is the mass of the object being orbited. So when you calculate Kepler's third law, we can write it now as removing the proportionality. We can write t square equals 4 pi square by gm times r cube. So this is the Kepler's third law. So Kepler's third law can also leads to an equation of period of an object in a circular orbit, and the speed of an object in a circular orbit depends on the same factors. So the time period can be written as t equals 2 pi under root r cube by gm, and the tangential velocity can be written as under square root gm by r. So where m here is the mass of the central object that is being orbited, and mass of the planet of the satellite does not affect its speed or period. Remember that m here represents the actual object that it's being circling around, so the mass of the central object that is being orbited, and here it does not get affected by either the mass of the planet or the satellite that is in the orbit. Now the mean radius r is the distance between the center of the two bodies. So based on the calculations from Kepler's laws, we can use Newton's law of gravitation and Kepler's laws and calculate the planetary data as shown below. So this is the planetary data for all the planets in our solar system, with the amount of mean distance, mean radius, and the mass of the planetary object. So let's take an example problem. So Magellan was the first planetary spacecraft to be launched from a space shuttle. So during the spacecraft's fifth orbit around Venus, Magellan traveled at a mean altitude of 361 kilometers. Now, if the orbit had been circular, what would Magellan's speed and period have been? So first things first, let's take into consideration the data that they have given. So the first thing they have given is r. So we have to calculate the time period and the tangential velocity. Now, they are talking about the actual object that it's circling is Venus. So let's take in the data first. So the r is 361 kilometers, so which can be written as 3.61 times 10 to the power of 5 meters. And now we have to calculate t and we have to calculate v. So from the Kepler's third law, we can calculate t equals 2 pi under root r cube by gm. Now the first thing that we need here is the actual mass. So the mass of Venus from this data here is 4.87 times 10 to the power 24. So m here is 4.87 times 10 to the power 24, and we have the g value, which is 6.673 times 10 to the power negative 11. This is kilograms, this is Newton meter square per kilogram square. And we also need to calculate R. So the R value is already given here, so we don't need to calculate the R value again. First thing to remember here is that we can consider this as R1. Remember that we are calculating the mean distance, so which means that here R2 is the actual radius of Venus. So the radius of Venus is 6.05 into 10 per times 10 to the power 6. So R2 is 6.05 times 10 to the power 6 meters. So we calculated the actual distance. So we have to calculate the actual total R. So the R value becomes R1 plus R2. R1 is 3.61 times 10 to the power of 5 plus 6.05 times 10 to the power of 6. So we can calculate this as 6.366. So this value becomes 6.41 times 10 to the power of 6 meters. So this is the R value. And we know the formula for Vt is square root of Gm by R. Now substitute all the values into the time period. So that becomes 2 pi times R is 6.41 times 10 to the power of 6 cube over 6.673 times 10 to the power negative 11 times mass is 4.87 times 10 to the power of 24. So now calculate the time period. So the time period becomes 5.66 times 10 to the power of 3 seconds. So this is the time period. Now we can also calculate the Vt value. So Vt is square root of Gm by R. So substitute the values. That becomes 6.67 3 times 10 to the power negative 11 times 4.87 times 10 to the power of 24 over 6.41 times 10 to the power of 6. So the tangential velocity here calculated becomes 7.12 times 10 to the power 3 meter per second. So this here becomes the tangential velocity. So we calculated the time period of the rotating object, and we also calculated the tangential velocity of the rotating object. So this is how we can solve the problem. Next, let's talk about weight and weightlessness. So to learn about apparent weightlessness, let's think that, imagine that you're in an elevator. Now when the elevator here is at rest, the magnitude of the normal force that acts on you is equal to your weight. Now, if the elevator were to accelerate downward at 9.81 meter per second, you and the elevator would be both in free fall. So which means that you have the same weight, but there is no normal force acting on you. This situation where there is no normal force acting on you results in an apparent weightlessness, and this situation is generally called apparent weightlessness. And astronauts in orbit generally experience this weightlessness because they do have acceleration, that they do feel the same, they do actually make the same way around the earth. So the more the force, the lesser the normal force, the lesser you feel the actual weight on your body. Next, let's go to section 4, torque and simple machines. So the objective here is to distinguish between a torque and a force, calculate the magnitude of a torque on an object, identify the 6 types of simple machines, and finally calculate the mechanical advantage of a simple machine. Let's start with rotational motion. So there are 3 types of motions that we are generally in motion of an object. So we can classify them into 3 types: rotational, translational, and vibrational motion. So we discussed translational motion. Translational motion is basically straight line motion, and rotational motion is the one that is to be analyzed. So for example, when you have a bowling ball that strikes the pins may spin in the air as they fly backward, These spins generally have both rotational and translational motion. So in this section, we will try to isolate only rotational motion and understand that specifically. So in particular, we'll try to measure how the ability of a force to rotate an object. So what is the magnitude of a torque? So torque here is the quantity that measures the ability of a force to rotate an object around some axis. Now, how easily an object rotates on how much force is applied and on where the force is being applied. Now, let's take an example here. Let's say we have an object right here that it's trying to rotate. Now, the distance here, let's consider this distance right here. So this distance right here is called as the perpendicular distance d. And let's consider that there is a force acting on this particular hinge. Let's, for example, consider this as a hinge. Now, this hinge is being acted upon by a force F. And the distance, the perpendicular distance from the hinge to the force here is determined by d. Now, this distance here and being applied at a distance, and there's a force, and this is the axis of rotation. The resultant is called as torque. So torque here is the product of the distance and the force. It's the vector cross product of distance and the force. And if there is an angle between the force and the distance, then the torque becomes Fd sine theta. Right? So if theta is 0 degrees, then the torque is 0. If theta is 90 degrees, torque becomes F times P. So this here is the two conditions that generally take into consideration. So which means that if the force and the torque are in the same direction, then there is no, so if the force and the distance are in the same direction, then there is no torque. For example, let's say if the force is applied in this direction and the displacement is also in the same direction, then there is no torque that actually happens on the object. So torque here is the ability, the torque here is generally given as the definition as the ability of an object. So torque is the ability to rotate an object by applying force. So this is the actual definition of torque. Now the applied force may act either at an angle, or the applied force might act always perpendicular to the distance. Now we only calculate the perpendicular distance because that is the only one that we need. So that's why we use the term Fd sine theta. Now the sign of torque. So torque here is also a vector quantity because it involves force and displacement. Now in this textbook we will use the term torque to deter each torque as a positive or a negative sign depending on the direction. So we always use the sign torque positive when the rotation is counterclockwise and negative if the rotation is clockwise. So let's take an example here. So a basketball is being pushed down by two players during a tip-off, and one player exerts an upward force of 15 Newton at the perpendicular distance of 14 centimeters from the axis of rotation, and the second player applies a downward force of 11 Newton at a distance of 7 centimeters from the axis of rotation. Find the net torque acting on the ball about its center of mass. So this is the ball consideration that we are taking into consideration here. So what is given here? A basketball is being pushed by two players during a tip-off. So let's consider a basketball here. So let's consider this is the basketball and this is the axis of rotation. Now what is happening here? For example, if this is the center of mass of the ball, what is given here? One player exerts an upward force of 15 Newton at a perpendicular distance of 14 centimeters from the axis of rotation. For example, from here you have 14 centimeters from the axis of rotation. So let's consider that this is 14 centimeters from the axis of rotation. And this is the first force, and this force is being exerted upward. And you have another force The second player applies a downward force at 11 Newton at a distance of 7 centimeters from the axis of rotation. So remember that a tip-off involves both players pushing on opposite sides. So which means here, let's consider that one player is pushing it here, and another player is pushing it here. So which means if you take the axis condition, so this is the condition. So this distance right here is 14 centimeters and this distance right here is 7 centimeters. So on one side the force being applied is 15 Newton, the other side is 11 Newton. So one side it's 15 Newton, the other side it's 11 Newton. Now we have to consider the actual net torque acting on the object. So the net torque, so let's consider the torque on each of these ones. So let's consider the first torque that is being applied, force times distance. Notice that here it's perpendicular, so the angle is 90 degrees, so we can write that it's directly FD. So F here is 15 Newton times 14 centimeters, which can be written as 0.14 centimeters. Now this is torque 1. Now we need to know whether it's positive or negative. Now if this is pushed, the actual body rotates counterclockwise, so which means that this is a positive torque. So this here is a positive torque. Now let's take in consideration torque 2. Torque 2 again is F times D. F here is 11 Newton times 7 centimeters, which can be written as 0.07. Now we need to know whether this is going to be counterclockwise or clockwise. So notice that here this force also turns it counterclockwise, so this is also positive. So we need to know the net torque. So the net torque is going to be the sum of the torques. Torque 1 plus torque 2. 15 times 0.14 plus 11 times 0.07. So this is the total torque. So which when calculated gives you a value of 2.9 Newton meter of torque. So one other thing to remember is that the units of torque is Newton meter. Right, so this is the final answer. Notice that both of them are going to turn anti-clockwise, so which means that both of them are going to give positive. So let's finally talk about the final topic, simple machines. So what is a machine? So a machine is a device, any device that transmits or modifies force, usually by changing the force applied to an object. Now all machines are generally combinations or modifications of 6 simple types of fundamental types of machines called simple machines. So what are these simple machines? First is a lever, second is a pulley, third is an inclined plane, fourth is a wheel and an axe, fifth is a wedge, and sixth is a screw. Let's start with all the simple machines and take a look at each of them. First is a lever. So a lever is, a lever. Here is a fulcrum. It contains a fulcrum, which is the fixed axis of rotation. And you have two sides where force can act on. And you have a wheel and an axle where you have a wheel and an axle. Axle is the fixed axis under which the wheel rotates. And you have pulley system, so you already know what generally a pulley means. And you have an inclined plane. Inclined plane generally is a plane at an angle where an object can move. And a wedge already obviously has an angle between them. And you have a screw which rotates helically. Now, all simple machines, because of the purpose of a simple machine is to change the direction or magnitude of an input force, and a useful way of characterizing a simple machine is to compare the output and the input force, and the ratio of this output to input is called as the mechanical advantage. Now, if you disregard friction, the mechanical advantage can also be expressed in terms of input and output distance. So, mechanical advantage is the outward force over the inward force, or the inward distance to the outward distance. Now let's take an example here. So the diagram here shows two examples of a trunk that is being loaded onto a truck. Now one way of doing this is either apply a large force upward to bring it to a distance d1 and push it forward, or you take a smaller force over a larger distance. Now notice that in both of them the amount of torque required is the same, but the difference here is the amount of force that required. So if you are applying a small distance over a large force and a large distance over a small force, which one would you choose? So you would always choose the one that has a lesser force because it requires lesser amount of force, therefore easily pushing the object. But notice that the amount of work done is exactly the same, 360 Newton meter or 360 joule. So because the amount of work done is the same, it doesn't matter how much is the actual force you apply. So therefore you will always choose the one that gives you the least amount of force, resulting in easier movement of the object. Next, let's talk about the simple machines efficiency. So we always consider simple machines to be ideal or frictionless, but real machines, however, are not frictionless. So therefore there is some input energy is dissipated as sound or heat. So we calculate the efficiency of a machine as the ratio of the output to the input work. So the efficiency of an ideal machine is 100% or 1, but the efficiency of real machines is always less than 1. So efficiency is the amount of output by the input. So this is the idea behind the efficiency of machines. So with that, we end the topic on circular motion.